Welcome. Today's notes worksheet is entitled Radicals. This lesson is certainly a continuation of yesterday's lesson dealing with square roots. We'll be using the exact same mathematics, except we'll be talking more with cube roots and fourth roots and fifth roots, and maybe seeing a couple other operations that go with this particular family of expressions. So I've got a couple investigations, of course. They should look pretty similar as we developed one with perfect squares yesterday. So we'll kind of dive into that and then just do some examples. Have a calculator handy if you would, so we can do some confirmation, make sure that as we rewrite some of these expressions that they are consistent. So the first investigation is dealing with perfect cubes. As you can see, we go concrete and then we go abstract on this. So number-wise, again, 1 is totally irrelevant in terms of helping us simplify, but obviously 1 is a perfect cube, should recognize that. And then I'll just throw a few out there. 2 cubed is 8. And maybe you can do some work on this as well. 3 cubed is 27. And again, half the battle, I think, with these, especially concretely, is can you recognize these values? 64 would probably be our next. 4 cubed. 5 cubed. 125. 6 cubed. How does 216 sound? 7 cubed, up to 343. 8 cubed. 512. 9 cubed, good one right there, 729. 10 cubed, 1,000. You know, and a little dot, dot, dot on that. I have a feeling we won't be seeing too many larger numbers. But again, should be able to recognize some of those perfect cubes. And then if you remember yesterday's lesson, then hopefully we can find a nice pattern for these algebraic expressions right here. What I'm looking for is just in a generic base x, what powers would constitute perfect cubes. And I'll, of course, get us going here right away. You know, x cubed is a perfect cube. Obviously, any number cubed, it would be a perfect cube. All right. Now, the question is, what is the next perfect cube? So if you remember correctly, we would think, you know, just in terms of the next, is x to the 4th a perfect cube? Is x to the 5th a perfect cube? Is x to the 6th a perfect cube, et cetera, et cetera? Think up the line there. Well, think about that. If you took a number to the 4th power, would it be a perfect cube? Nope. If you took a number to the 5th power, pick a nice easy number, would it necessarily be a perfect cube? Nope. How about to the 6th power? What if I took 2 to the 6th? 2 to the 6th is 64. That's actually on our list. That's a perfect cube. 3 to the 6th, as a matter of fact. 3 to the 6th would actually be 729. Ooh, that's a perfect cube. Yeah, actually, as a matter of fact, anything to the 6th would be a perfect cube. All right, now maybe you can catch the pattern here. What would be the next perfect cube? Working up our list here. X to the 3rd, x to the 6th, x to the 9th, as a matter of fact. And what you're going to see, long story short, is that these kind of go up in 3s. All right, I'm going to dot, dot, dot that right there, and that's looking great. Let's confirm on the calculator with a couple things, and then if we need to kind of go back into this piece, we will. But let me bring my calculator up, and if you can do the same, that would be great. And let's confirm. So basically, I had said that anything to the 15th, here I'm just picking one that I see, anything to the 15th is also a perfect cube. So let's test that out. So let's do 2. 2 raised to the 15th is that number right there. Now 32,768 should be the perfect cube of some particular number. Let's find out what it is. By the way, again, just getting used to these calculators, let's find cube root for the first time. Everybody, cube root is under the math menu. Find math. For me, it's the 4th one down right there. And so I'm going to go ahead and hit that. And the cube root of that answer, by the way, to get answer, I hit second and then the negative button. Otherwise, you have to retype. But regardless, cube root of that, and there you go. So the cube root of this is exactly 32. This is the perfect cube of 32. Wonderful. Would that work for any other base? Yeah, sure. And let's pick another one. Let's do different base, and let's do different number. How about something like this? Anything to the 12th should be a perfect perfect cube. So how about 5 to the 12th? Just making up numbers. Yikes, fairly large number there. But regardless, this value should be a perfect cube. So let's do the cube root. So math, get me cube root of that answer. And what cubed would give me that? All right. So this is the perfect cube of 625. Excellent. And so you can kind of see, and I could do this ad nauseum here, but anything raised to these powers would be a perfect cube. Just real quick, if I asked you for the cube root of each of these, could you pull it off? I hope so. X is what's being cubed to get that. X squared is what's being cubed to get that. So if I asked you the cube root of x to the 6th, you would tell me x squared. Keep that in mind. You're going to need it. What's the cube root of x to the 9th? Well, it should be x cubed. What's the cube root of x to the 12th? X to the 4th. And you can kind of see the pattern in action. I'm just going to dot, dot, dot this. And if you're not understanding that piece, please call me over. All right, let's go fourths. We'll go up to probably fifth roots on this, and I'm not going to do an investigation on fifths, but you can use the same premise. So fourths, guys. 1 to the 4th, again, irrelevant, but it is. 2 to the 4th, 16. 3 to the 4th, 81. 4 to the 4th, 256. And by the way, do you remember yesterday's lesson? We said anything to the 4th is a perfect square. That's a perfect square. That's a perfect square. That's a perfect square. This is also. This would be 16 squared. So all of these are also perfect squares. All right. And let's see, get a couple others on there. Obviously, we're not going to go too high in, but something like that would do. Not a problem. What would the pattern look like in algebraic expressions for fourths? Let us see it in action. Hey guys, x to the 4th is obviously the first one. Anything to the 4th, by definition, is a perfect 4th. Now, you've seen the pattern on the squareds. You've seen the pattern on the cubes. So use that to extrapolate here a little on the pattern for the 4ths. X to the 8th would actually be the next perfect 4th. Any number raised to the 8th would be considered a perfect 4th. Anything to the 12th, anything to the 16th, etc., etc., etc. If I asked you for the 4th root of each of these, could you pull that off? So what is it that's being raised to the 4th? Here, obviously, it's x. What is it that's being raised to the 4th here? X squared. 2 times 4 is 8, of course. What's being raised to the 4th right here? X cubed, etc., etc. Hoping that makes pretty good sense. And you're just seeing great number theory in action with these. Let's confirm on the calculator one last time, and actually kind of a new function or new button to kind of look at here. So let's go ahead and look at it. So what I basically said is anything raised to these powers should be a perfect 4th. Let's test. So, oops, how about something like this? I'm just going to make stuff up. How about 3 to the 12th? That should be a perfect 4th. So this is some value raised to the 4th power. Let's see what it is. So here's how we do a 4th root, everybody. Again, you're going to have to be doing these over the course of the year. We actually hit the number 4 first. Then we go under the math menu. And you see right underneath the cube root is the x root. So let's go ahead and hit that. So this tells me I want the 4th root. And then let's just put in our number, 4th root of that number. And notice, this is a perfect 4th of 27. 27 to the 4th is this. Okay, would that work with anything on this list here? You bet. I hope you really do see that at this stage. Okay, good. Nice little list. I think that'll help us really simplify these. Just put an asterisk, if you would, next to this. Product property, quotient property works out the exact same way as with cube roots and 4th roots and 5th roots as it did with square roots. One additional property here, I probably won't go over this in too much detail, kind of the root underneath the root. And the way this works here is, as you can see, the mth root of the nth root of a is really the m times n root of a. So long story short here, let's see if we can see this in action concretely. If I asked you for the cube root of the square root of 64, well, cube root and then the square root being underneath, square root of course is a 2 right here, 3 times 2 is 6. That should be equal to the 6th root of 64. And so I guess let's do this numerically. Hey guys, what is the square root of 64? 8. So the inside expression is just 8. And the cube root of 8, of course, is 2. So that's our answer right there. And again, based on this piece, 3 times 2 is 6. That should be equivalent to the 6th root of 64. So can you think of a number raised to the 6th that is equal to 64? And it's 2 to the 6th. So the 6th root of 64 is 2. Okay. Again, we're not going to see that a lot. All right, let's try it out. So I'm going to follow a very similar format to yesterday, just on the examples 1 and 2 that you see on your paper. So really just working with the product property and quotient property if it comes up. And I'm going to go ahead and get my perfect cubes in 1. In fact, I'm going to write that for the first time here. So perfect cubes in one radical, remaining factors in the other radical. And this should work out pretty nicely for us. So here's what I'm thinking. Let's create a radical cube root. And let's see, what is the perfect cube that goes into 40? So there was a reason for us developing those lists that you see at the top for this purpose. So look at the list. What number goes into 40? 8, of course. So 8 goes into our 40. So I'm going to put that right there. And then again, product property says we can split this up into 2 cube roots. Cube root of 8 times 5 is really the cube root of 8 times the cube root of 5. And what is the cube root of 8? Cube root of 8 is 2. So that value comes out, and so I get 2 times the cube root. And please don't forget to actually put this as a 3 right there. I've seen a lot of students over the years kind of forget that. And obviously, a square root would be different than a cube root. So 2 times the cube root of 5. Nice. And that's it. That would be the simplified version of this, still keeping it in exact form. Pulling out the perfect cubes. Product property it is. Let's do it on the fourths. So same deal. Perfect fourths in one, remaining factors in the other, and then we simplify this one right over here. Look at the list, everyone. What's the largest perfect fourth going into 48? I'm seeing it as 16. And 16 times 3 would do the trick right here. And so what we should get is 4th root of 16 is definitely 2. And then times 4th root of 3. And that's pretty much how we would leave it. Pulling out the perfect fourth out of 48. By the way, just very, very quickly, again, you notice I've gravitated nicely towards this particular method. But do you remember I told you the dating method on the previous lesson where couples get to go out? You can do the same thing here, except trios get to go out. I might do that very fast for you just so you can see it. And here, in this case, groups of 4 can go out, and everybody else has to stay home. So watch, we have just a sec here. Why don't I just do this real quick? Just kind of show you what I mean. So 2 times 20, circle the 2. 2 times 10, 2 times, oops, let's erase that. So 2 times 5 on that 10, which would suffice. So 2 times 5, and then as a trio, the 2 can go out. And anything else has to stay home. Pretty cool. It works the same over here. Groups of 4 can come out. Everyone else has to stay home. Again, you can use that or not use that. You see the method I've approached it with, really just understanding perfect cubes and fourths and so forth. Okay, let's go do 2. A little more abstract here, but use that list from above. Let's go get them. Perfect cubes in 1. Product property, remaining factors underneath the other root. So let's take it numerically first. 16. Perfect cube going into 16. 8 and 2. So 8 times 2 should give us that 16. Now here's where you come in, please, if you would. Write it down before I say it. What is the largest perfect cube that goes into x to the 4th? So you look at that list. Well, x cubed goes into x to the 4th. And x cubed times what would give me that x to the fourth? Has to be x to the first. Is that okay? So perfect cube in here, and that's why we made that list, to make this nice and easy for you. Now think about this. What's the largest perfect cube going into a base to the seventh, the y to the seventh? Well, the largest number underneath 7 on that list was 6, y to the sixth. And y to the sixth times y would be y to the seventh. So perfects in here, leftovers in here, clean this up, and we're in business. Cube root of 8, 2. Cube root of x cubed, as we determined above, is x. Cube root of y to the sixth, or really, what cubed would give me y to the sixth? As we determined, y squared, if I cubed it, would give me y to the sixth. That I want you to see, make sure you understand that piece, and if not, let me know about it. And in times, there we go. Again, just very abstract expressions there, just manipulating variables and working with them in terms of radicals, roots, basically. Okay, good. Let's go get this one right here. This is a good one. We saw one like this yesterday, so should be all right. I would say, and again, this is just my perspective on it, it's easier to put things together ourselves, even though we're kind of building these up for a minute, and then break them apart the way we want to, as opposed to doing this independently. I wouldn't do this one, simplify, and then this one, simplify. And I don't know, you can. I'm going to put them together under one root. I like seeing it in one particular way and then working at it from there. Long story short, what I mean by that is product property says I can do 32 times 4, 128. X to the sixth, y to the 10th, and z to the fourth. So just being able to work with those variables and the powers, of course. Got to know those exponential properties. Now let's go ahead and take this piece and break it apart the way we want. So what I'm thinking is perfect cubes in one, remaining factors in the other. Is everyone okay with that premise? So we kind of go through concretely and then more abstractly on these variable powers, and let's see if we can pull it off. I like a 64 times 2 split right here. So 64 and 2 I think works out really quite well. Now again, use the list from above. That was kind of the reason in seeing the patterns and in confirming those patterns. X to the sixth is a perfect cube, so it's going to go in. What's the largest perfect cube going in y to the 10th? I see it as y to the 9th. We just want the largest power that is equal to or below this right here. And y to the 9th times what would give me y to the 10th? It would just be y to the first. And then same here, what's the largest perfect cube going in z to the fourth? I'm hoping at this time it's really clicking, and so I'm seeing a z to the third, and z to the third times what would give me that z to the fourth? Z to the first. This is awesome. It can be simplified. This is what's going to be remaining. Let's go get them. What cubed gives me 64? 4. What cubed would give me x to the sixth? X squared. What cubed would give me y to the 9th? Y to the third. And what cubed would give me z cubed? Well, of course, z. There you go. And in times this piece right here. And there you have it. Great. Good, good, good. Let's keep it going. I have an investigation here that kind of leads us into our kind of last operations. Hey, just addition and subtraction. What works numerically? What doesn't work numerically? Let's just make sure we see what this means and how this plays out. So guys, let's grab a calculator. Very simply. Does root 2 plus root 3, does that equal square root of 5? Now don't write this on your paper because remember, root 2 times root 3 does equal root 6. Absolutely. That is something we developed. There is the product property. I guess the question is there a sum property? So let's find out. Grab your calculator for me. I'm going to go ahead and get mine right now. So let's see. Let's get that root 5 going. Here's root 5, about 2.24, give or take. Now let's see what square root of 2, close it, plus square root of 3, is it equal to it? No, as a matter of fact, not equal. So can I just add the numbers under the root? Absolutely not. So there is a product property, no sum property like this right here. Does not work. Not algebraically legitimate. What about this one? I don't know. Let's see. Cube root plus a square root of 2, is that equal to the 5th root of 2? Now let's give it a try. Good practice on just working with these. So cube root. Remember, cube root is right here. Math. Cube root of 2. Plus, and let's do square root of 2. So the 3 and the 2 there on the roots, I get that. Is that going to be equal to the 5th root of 2? You know, I'm just trying to think. 3 and the 2, can I combine those together and make this a 5th root? Hey guys, let's hit the number 5. Go back to math. There it is. There's the x root. So 5th root of 2, not even close. So is that something we can do? No. All right, so we're going to have to be a little careful when working with this. One more question and a conclusion to put this together. And this is an interesting little expression. What does 2 root 5 mean? Well, this would be, what does 2 times the square root of 5? Well, remember everyone, of course, multiplication is just repeated addition. So 2 times the square root of 5 is really adding 2 root 5s together. So this, I'm going to just kind of circle this and think about it this way. This, everybody, is 2 root 5, right? Now notice what's in between. There's a plus. So let's put a plus in. Hey guys, what does 3 root 5 actually mean? Well, 3 root 5 is, again, 3 times square root of 5. Multiplication is repeated addition, so this would mean adding 3 root 5s together. And there you have it, adding 3 root 5s together. And what would that be equal to? Well, repeatedly adding 5 root 5s is, hey, go figure, 5 times the square root of 5. And so you can kind of see that this is equal to this right here. A different approach, of course, and we've seen this before, I'm going to do it above, is factor it. Look at this, guys. Watch this. Look at that piece and that piece. Do you see square root of 5 is in each of those? What happens if we pull out square root of 5? Well, from here I would get a 2. From here I would get a 3. And do you see if you simplify, 2 plus 3, of course, is 5. So is this equal to 5 root 5? You bet. And so can we add radicals together? Yes, but we have to be careful. So here we go, conclusion. So combine radicals with the same root, and there's probably some more technical ways to talk about this, but I think this is a little better for us. They have to have the same root and the same term. So that's the key right there, guys. As long as they do have the same root and the same term underneath, we can combine them together. If they don't, very simply, we can't. There is no sum property if they are different terms under the root, and there is no sum property if they are different roots themselves. Okay, so let's go ahead and do a couple examples and round this out for you. Example 3, good stuff. Just again, manipulation, in this case, operations. So let's do some addition and subtraction. Can I combine these together? Sometimes the phrase I'll use is this apples to apples? Yeah, definitely. I have 2 cube roots of 4. I take away 3 cube roots of 4, and so I get negative 1 cube root of 4, and that is as quick as these problems get. Awesome. So negative 1 cube root of 4. All right. Now, letter B, at first glance, you're thinking, wow, I can't do cube root of 24 minus cube root of 81. Can't do it. Let's move on to the next problem. Well, before we decide to do that, we should investigate this in a little detail. Can I simplify each of these roots a little further? And the answer is yes. So I'm going to go ahead and simplify, dealing with the idea that let's see if we can pull out the perfect cube going into 24. And I hope you would all agree that's probably 8. So cube root of 8 times cube root of 3. So this works for the cube root of 24 using the product property. And then minus a factor of 2. Same thing on that 81, everyone. There is a perfect cube that goes into 81. Definitely want you to be able to recognize that piece. And I'm seeing this as a 27 times 3. Okay, good. Now we work through. Just good numerical calculations here. And let's simplify. Cube root of 8 is 2. So cube root of 3. Here we go. Cube root of 27 is 3. And then cube root of 3. All right, now, again, let's keep working. This expression right here is a product of these factors. Let's go ahead and put those factors together. 9 times 2 is 18. 18 cube root of 3. 2 times 3 is 6. 6 cube root of 3. And when all is said and done, 12 cube root of 3 is the exact same numerical value as what we started with. Obviously, nice and simplified, looking good. Cool. So don't just let it go. Make sure you go ahead and look at that piece in a little detail and see if you can go ahead and combine. All right, let's do letter C. Interesting one here. Got some variables in action and so forth, so let's see what happens with this. All right, so let's see. I'm going to pull out perfect cube on this one. I see 8 is a perfect cube. What is the largest perfect cube going into x to the 4th? X cubed, right? So x cubed times x. Interesting. And then I have a cube root of x right here. Yikes, not much I can do there. And then let's see what's going on here. In this one, I've got a factor of 4. 27 is a perfect cube. So let's put that in that one right there. And cube root of x really can't touch. Hope everyone recognizes that. Look at that breakdown. Make sure you kind of agree on the product property, especially the first term and the third term. Look at that in a little detail before us moving on. Okay, well now let's see. Cube root of 8 is 2. Cube root of x cubed is x. So I have this. Okay. Now this is going to seem a little strange, but plus cube root of x, I'm going to put a little 1 out there. I don't know. If you forget to do that, you might overlook something. But I do have officially, I'm adding 1 cube root of x, so I should acknowledge that at least. And then over here, if you don't mind me skipping half a step, cube root of 27, of course, is 3, and 3 times 4 is 12. So I'm getting 12 cube root of x. All right, so you can see this one is quite a bit more abstract than letter B, but the question remains, can I combine those together? Absolutely. So I have this many cube root of x's plus this many cube root of x's plus this many cube root of x's. And again, if you kind of think about that factoring out the cube root of x, it would work. But how many cube roots of x do I have when I add all these together? I have 2x plus 1 plus 12. Oddly enough, guys, this seems a little strange for an answer, but that's what I'm getting. That's how many cube root of x I would see. I showed you kind of factoring the cube root of x out would work, you know, like I did before. And if you factor out a cube root of x from each of those terms, you could see I get that times 2x plus 13. All right. Weird answer, but correct and fairly simplified nonetheless. Pretty cool. All righty. Let's go get the last piece. So we rationalized on the square roots. Cube roots and fourth roots are going to be a little harder. I guess let's have a goal here. And so I'm going to go ahead and write this. Our goal is to create a perfect cube or fourth, whatever we're talking about, or fifth, etc. there, etc., in the denominator. Alrighty, excuse my shorthand there, ran out of room. So I think that's what we're going to do. In order to rationalize the denominator, I think what we're going to have to do is treat it in a slightly different way. And I'll show you what I'm thinking in just one sec, but make sure you have that piece down. So if this was square root of 2, you would just say, oh, all I have to do is multiply it by square root of 2, and go to town on it, and you'll get it. And if you do the same thing here, if you're like, oh, all I have to do is multiply it by cube root of 2, the question is, does it work? Well, if I really do this correctly, the top is not an issue for me. And by the way, please don't write this down. I get cube root of 2 on top, and really, product property would tell me to do cube root of 2 times 2, which is cube root of 4. Wait a minute, guys. Is this a rational number? No. 4 is not on our list. So by just multiplying it by the same term, like we did yesterday with the square, it doesn't quite work. So there are a couple ways to do this. I'm going to try to streamline this a little bit for us. But ultimately, our goal is to create that perfect cube down in the denominator. So I guess what I would do, and again, it's just good number theory, 2 times what would give us one of the perfect cubes down on the from our list? Well, 2 times 4 would give me 8. And so as a result, I think that's our winner. Okay, and so when we do this now, I get cube root of 4. Cube root of 2 times cube root of 4 is cube root of 8, and cube root of 8 is 2. And there you go. Remember how we kind of talked about this? This is really division, and the way we talk about division is you have a finite length divided into a countable number of pieces. So when I have the cube root of 4, I'm going to divide that into 2 pieces. This does not quite make that sense. It doesn't kind of work the same way. So here, you're rationalized. I've seen students over the years, by the way, and again, I'm always just trying to give you different ideas. You know, it's kind of weird, but you know, since it's a cube root, you can do it twice, you know, something like this. So now here would be your cube, essentially. It times itself, right? And so if you do that, guys, would you get the same answer? Yeah, you would. I tried to do it in one shot. Here's your cube root of 4, which is kind of like this right here. But this is, in essence, what you're doing. But instead of multiplying it once like we did yesterday, we have to do it twice. Weird. Okay, let's see. So what I would personally do is see what we can do with this. You can simplify this root, by the way. But I'm going to go ahead and just try to create the perfect root. So in this case, I'm thinking 16 times 4 would give me 64. 64 is a magic number for cubes, so that's a good one to shoot for. And so 16 times 4 would do the trick. And whatever I do to the denominator, I do to the numerator, and I get 6 cube root of 4. And guys, notice here 16 times 4 is 64. Cube root of 64 is 4. And does it simplify? Yeah, a little bit. So how about we do 3 cube root of 4 and then over 2. Perfect. Okay, again, you can find ways around this. I've seen students over the years kind of break that down as this would be 2 cube root of 2, because 8 times 2 is 16, and 8 is a perfect cube. And then could you eventually get the exact same thing? Yeah, sure. Again, go with what works for you. I watched this one. This is a great one right here. So how do we do it with a perfect, or to create a perfect fourth? So again, product property, fourth root of something, I'm thinking here, and let's see if we can make it happen. Look at the list, everyone, of perfect fourths. Quickly flip, and then come on back. Is there a number that is a perfect fourth that is evenly divisible by 9? So 9 times something would give it to us. Well, I think the perfect fourth we would look for there is probably 81. I think that's the one on the list. And 9 times 9 is 81. I saw that. See if you can find a way around that as well. But I think that should give it to us, because now I've got 3 fourth root of 9. This would be the fourth root of 81, and the fourth root of 81 is 3. Hey guys, these cancel, and there's your answer. Beautiful. So let's box up everything there, and we've got our winner. Okay, so kind of wrapping up the family of radical expressions and working with those and performing operations on them. Let me know if I can be of assistance as you try some of these problems out. Thanks so much for listening.